so I'm going to talk about the basic concepts of our method for expression of entities. This is a scheme of conventional methods of fusion technique for producing inclusion body. In the conventional method, aggregation from protein used for fusion partner for the target peptide expression. And the conventional method, after solubilized in under denaturing condition, you have to create the fusion partner from the target peptides. So in our new method, co-expression method, we utilize aggregation from protein as partner protein for co-expression of target peptides. In this system, you don't have to create target peptide from partner aggregation from protein because they are not connected covalently. So it's very simple. Okay. In order to check our concept work well or not, we select the target MP derived from nematode. Okay. Target peptide is antibacterial factor ABF derived from C elements. This is a very small peptide and highly basic peptide. The PI of this peptide is 9.1, and it contains 8 cysteines and 4 disulfide bonds. And it is predicted that this peptide form insect definition type 4, but it is difficult to prepare the sample, so there are no structural analysis of this antimicrobial peptide from C elements. Okay, so we selected human alpha-lactoalbumin. It is well known as aggregation from protein for co-expression partner, and we used PET or PCOL vector as a co-expression system in IGRI. Okay, I'm going to show you the result. This is the result of our experiment, and you can see clearly ABF did not express at all without partner protein, but you can see with HLA aggregation from partner protein, you can see the band of ABF clearly. So co-expression of aggregation from partner protein clearly enhances the Y-expression level of target peptides. Okay, in order to analyze the factor influencing inclusion body formation, we choose alpha-lactoalbumin and ribosome superfamily protein as partner protein. All of them form inclusion body, and they share high sequence and structural similarity. However, the PI is varying each other from 4.9, 4.7 to 9.3. So this is very good model for factor influencing inclusion body formation. Okay. And yes, we can clearly see that acidic partner protein, like human array and bovine array, clearly enhanced overexpression of target peptide. On the other hand, neutral or basic aggregation from partner did not enhance overexpression level of target antimicrobial peptides efficiently. So acidic partner proteins enhance expression level of basic target peptide. Okay. I'm going to show you example of other targets. Okay. This is the antimicrobial, other antimicrobial peptide and DNA-binding protein, relatively big. And in the case of these basic target, acidic partner enhanced expression. And in the case of the acidic target, this is protein from thermophilic bacteria. Yes, this is a small peptide from thermophilic bacteria, and the value is 4.1. In that case, acidic target, the overexpression level of the acidic target clearly enhanced by basic partner. Okay, so this method can be applied to both acidic and basic targets. Okay, so I'm going to mention about the most important merit of our new system. Purification system of our expression system is very simple. After correction of IV, after solubilization, we can use cationic exchange chromatography and separate MP and partner protein easily, because the charge of the target and aggregation from partner is opposite, so it is very easy for us to separate two molecules. Okay, this is expression and purification step of ABF. We can obtain a lot of crude ABF from E. coli, but in the case of ABF contains many cysteines and disulfide bonds, so we have to optimize the refolding condition of this antimicrobial peptide. So if this protein, this peptide is 7.8 milligram per 1 liter of every culture. After refolding process, we characterize target antimicrobial molecule by using 3D measurement and by the assay of antimicrobial activity. These results really show ABF reported correctly, we think. Okay. And after the production of ABF, we move on to structure analysis of ABF by using NMR. This is HSQC spectrum of ABF and the result of structure analysis of ABF. So we can utilize a new method for producing isotope-labeled sample for NMR analysis. Okay, I'm going to talk about other application of this method for producing mouse cryptidine. Target peptide protein 4, CRP4, is MP derived from small intestine from mouse. This is a small and highly basic peptide, and it contains 6 cysteines and 3 disulfide bonds. It belongs to alpha defensive family. Oh, sorry. This is a result of our experiment, and our method to clearly enhance the expression levels of CRP4, and yes, we can efficiently use this method for NMR analysis. And we recently get surprisingly result about the producing of CRP. In the case of CRP, yes, in the solubilization process, ordinary condition for solubilization, we use milk cup ethanol, but we modify the condition of solubilization step without using milk cup ethanol. Yes, we can recover CRP4 without refolding step. Yes, we surprised that result because usually we need refolding process for producing cysteine-rich antimicrobial peptide. But in the case of CRP4, CRP4 can refold correctly in its solubilization process without refolding step in denaturating condition. So we are very surprised, but we can efficiently obtain CRP4 by using this method. Okay, this is the conclusion of my talk. For expression and aggregation from protein can enhance overexpression level of small peptides, and isotope point of target peptides and partner proteins are important factors for formation of ID in our co-expression method. We can utilize this method for producing isotope-labeled sample for animal studies, and in the case of CRP4, it forms correct disulfide bridges under denaturing condition. Okay, this is acknowledgement for collaborators, especially Professor Kawano. Thank you for my many thanks for Professor Kawano for many advice for our expert. Okay, thank you for your attention.
The presentation is open for questions.